Chapter 9, Section 9, the next to last section, wherein we've learned some rules about writing Lewis structures, and now we'll talk about exceptions to the octet rule. Now, focus on the rules, okay? We got to learn the rules before we can break the rules, and most of these exceptions to the octet rule are things that we already learned, okay? For example, the first one, the incomplete octet. If you have an incomplete octet, if you don't satisfy the octet or the duet rule, things are not going to be particularly stable, okay? So hydrogen and helium get their duet, but for example, beryllium dihydride doesn't, BF3 doesn't. So we have these examples where if we draw a Lewis structure, you can get 4 electrons around beryllium. You can get 6 electrons around boron. These compounds are not stable. Boron is a very unusual element in that it often bonds this way, but the compounds that it forms are not stable, so they tend to dimerize. 2 of them get together, so that boron, in fact, effectively does have 8 electrons around it. It's just a matter of boron only starts with 3 electrons. It doesn't form ionic compounds like aluminum, and so when it tries to share electrons, you end up with these weird, unstable, incomplete octets. Fine. Another example would be odd electron structures. When nitrogen forms compounds, it starts with 5 dots, okay? If it only forms a compound with 1 element, like in NO, you end up with a radical. NO is not a stable compound. Now the final one, though, the final exception to the octet rule, the expanded octet, that one is ubiquitous for elements that are lower on the periodic table than that second row. Okay, hydrogen, helium, that's the first row, and then we got the row going across up to neon, all right? That row where we have 2p elements, there are no 2d electrons. Okay, when we talked about Lewis electron configuration, no 2d electrons. 3p elements, on the other hand, have empty 3d orbitals. 4p elements have empty 4d orbitals. We haven't gotten there yet, right? Because that's the problem with that middle of the periodic table, right? Is you start 4s and then you go to 3d. You start with 5s and you go to 4d, etc. So you have empty d orbitals that larger elements, not carbon, nitrogen, oxygen, fluorine, okay, that the larger elements can use. We have empty d orbitals. So, for example, SF6, you draw the Lewis structure. Oh no, 12 electrons around sulfur. Totally allowed. It's going to use its d orbitals. Now, 8 electrons, stable. 10 electrons, okay. 12 electrons, okay. Beyond that, you start to get crowding. It's just physically too crowded around that central atom, and you can't cram more around there. Are there people out there breaking the rules? Absolutely. 18 electron structures have been made. For us, you draw a structure, you get 10 or 12 electrons, okay. Beyond that, probably not okay. That's my warning to you. If you get a structure with 14, 16, 18 electrons around a central atom, you probably have not broken the rules properly, okay? 10 electrons for sulfur or phosphorus, 12 electrons for sulfur or phosphorus, very, very, very common. Why do I bring up those elements? Because they're important biologically and you're going to run into those often. So, that being said, let's try a couple of problems here. Oh wait, just one more time. Here we go back here. SO2. If you look for how to do the Lewis structure of SO2 on the internet, pretty much every single video there is wrong. I don't love your book's picture, but I took I had a footnote there that I took off. Everyone on the internet says that SO2 is like ozone. Ozone has a double bond between 2 of the oxygens and a single bond between the other oxygen because oxygen cannot violate the octet rule. Okay, no expanded octet for carbon, nitrogen, oxygen, fluorine. Period. End of story. Okay, you can't do it. There are no d orbitals to use. It is not possible. All right. S, on the other hand, can violate the octet rule on the high side, as I want to say. You can have 10 electrons or 12 electrons for sulfur. So, that being said, does sulfur with 2 oxygens bond like oxygen with 2 oxygens in ozone? In fact, it doesn't. There's no way that we can know this ahead of time. We would draw our Lewis structures and we would get one structure that has, let's see if I can get the pen to work today. Screen draw, pen, right? We end up with one structure that has this in the middle. And we have one structure that looks like ozone in the middle. That's a resonance stabilized, all right? Multiple correct Lewis structures where we have the single bond on one side and the other one on the other side. Okay, with of course enough, lone pairs to make oxygen good. All right, which one is it? Is it the double bond or is it the resonance stabilized ozone-like structure? And the answer is, to predict it, you don't know. But if you go to the experimental evidence, look at the bond lengths, which is what we're going to talk about in the next section. It is a double bond. It is not like ozone. So don't trust everything you see on the internet, as if I had to let you know that. All right, so here's one for you. You won't be able to enter this answer into the answer palette because you can't draw in it, but maybe I'll put up some choices or something for you. Draw the Lewis structure. I'll try it on your page for aluminum triiodide. And I point out at the bottom that aluminum triiodide, just like boron trihalogen compounds, tends to form two linked together so that it will satisfy the octet rule. But aluminum triiodide, try it and you may find out that it does not. And I gave you the Lewis structure, or the ball and stick model there, so I kind of made it a little bit easier for you. But if you, if you draw it out, let's get this screen draw going again. You would have 3 dots on aluminum. There's one, there's one, there's one. Your iodines would each have 7 dots, right? Right? And then you connect your dots. So it actually looks just like the ball and stick model that I gave you, right? 1 line in between each, and 3 lone pairs on the iodines. Okay? All right. Next one. Draw the Lewis structure for phosphorus pentafluoride. Okie dokie. Just like with the last one, you put your 5 dots down for the P. You put your 7 dots down for each F, and you connect the dots, and you end up with 1 line between each F and the P, and no lone pairs on the P. And you violated the octet rule with 10 electrons around P. Totally allowable because it is not a 2p element. It is lower down on the periodic table and therefore has vacant d orbitals that are low enough in energy for it to use. I mean, hydrogen has vacant d orbitals. They're just so high up in energy it can't use them. 2p elements would have 3s, etc. orbitals that are empty. They're just too high in energy to be used. Okay, but phosphorus can use its d orbitals because they're close enough in energy. One more question for you. Draw the Lewis structure for a sulfate ion. This one won't exactly match the ball and stick model that I've given you. Take a moment and see what you can come up with. Okay, when you do the Lewis structure for SO4, you can have some double bonds and some single bonds in some different places. Okay, you put your sulfur down. You do your 6 dots. 1, 2, 3, 4. 5, 6. You put down your oxygens. 1, 2, 3, 4. You put your 6 dots for each O. 1, 2, 3, 4, 5, 6. I'm not doing it in the proper order, I know. 1, 2, 3, 4. I'm not keeping my electrons as far away from each other as possible, but I know where they're going to go, so I'm predicting. If we did it right, here we go. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Connect the dots. Connect the dots. Oops. Connect the dots. Connect the dots. I forgot something, didn't I? 2 minus charge. Extra dot. Random choice of which oxygen. Extra dot. Random choice of which oxygen. I'm going to connect this dot and this dot. Yank. I'm going to connect this dot and this dot way over here. Yank. Okay? And what do I have? All right, cleanup step. Make it look pretty. Sulfur. Double bond over here, double bond up here, single bond, okay? That's what I got doing it this way. 2 lone pairs, 3 lone pairs on the single bonded oxygens. Oxygen satisfies the octet rule as it must. Sulfur doesn't satisfy the octet rule, right? It's got 2, 4, 6, 8, 10, 12 electrons around it. That's cool, that's fine, no problem, totally allowed. What is not allowed, what is not going to work very well, is if you did this. And the only reason I can explain to you why it's not like this is because of experimental evidence. We look and we see, does this sulfur oxygen polyatomic ion called sulfate, does it have resonance stabilized 1.5 bonds, right? Because we could have the double bonds here, we could have 2 there, 2 there, we could have any possible combination of 2 double bonds and 2 single bonds. So we have a 1.5 bond. All the oxygens are in fact identical in here. That's true from experimental evidence. Then the question is it SO double bond length or is it SO 1.5 bond length? And the experimental evidence shows us it's 1.5 bonds. So then we need to devise a hypothesis for why this is true. And having 2, 4, 6, 8, 10, 12, 14, 16 electrons around sulfur is just too many. Sulfur is big, but it's not that big. You can't cram that many electrons around a sulfur. It's just not going to work. So it is not this one, okay? It's perfectly tetrahedral because of the resonance. They are all equal bonds, 1.5 bonds. There's just no good way of drawing that in a Lewis structure. All right? It's not this. These bonds are too long for that. They are too long for that, as we will discuss in a little bit more in the next section. One more. Ba-bum. Put these up there so you can read more about it, what I just said. XeF4, xenon tetrafluoride. Give that one a whack and see what you come up with. Okay, xenon is already a noble gas. It's a stable compound. It's a stable element. Why would it form compounds? Well, you mix it with fluorine. Fluorine is incredibly electronegative, right? Most electronegative element on the periodic table. It's very harsh conditions. This isn't done at room temperature either, I'm sure. It's got to be high temperature to get the xenon to react. Xenon's a big noble gas. The electrons that are filling that outer valence shell are nice and stable, but they're very, very, very far away from the nucleus. So when you draw the Lewis structure, you end up with a compound that has more than an octet because it started with an octet. That's okay. Xenon is not helium, okay? It has empty d orbitals that it can use to form bonds and to put lone pairs in. All right? That is the end of section 9.9. Final section in the next video.